In this video, we're going to look at some terminology and look at a little notation. We're going to explore an alternative definition of the derivative and then rework a problem we've worked before using that alternative definition. So first of all, you can see here that we have terminology here, number one. So if the derivative exists, so if f prime of x exists, and here again, think of x as a fixed value, any fixed real number. So if that derivative exists at some x value, then we say that the function f is differentiable at x. And you can see there in my note there, again, we're thinking of x as fixed. So for any fixed x, if the derivative exists there, then we say that f is differentiable at x. And number two here, if f prime of x exists at every point in the domain of f, then we say simply that the function f is differentiable. So there's just some terminology there. Now let's look at some notation for the derivative. So again, here are we're looking at our y equals f of x, so here. And so we already know the first one, f prime of x is one way to notate the derivative, but let's look at some others. So this second notation, dy dx, we use that to emphasize that y is a function of x and that we are taking the derivative with respect to x. Okay, so that's that. And then another common notation, particularly if your f of x, if your function is pretty complicated, then we'll just do d over dx, and then in brackets we'll put the expression or whatever we're taking the derivative of. So this notation here, we're saying we're taking the derivative with respect to x of, and then what's in brackets. We can also just consider y to be our function and then just do y prime of x. That's another alternative. And then the last one, it may not be as common, but you will see this from time to time, this capital D operator and then the subscript x, which again emphasizes that we're taking the derivative with respect to x, and then just as we saw before, we're taking the derivative of what's in brackets there. And sometimes you may see parentheses used here instead of brackets, but it's the same thing. So there again, just a different notation for the derivative that you may see. And like I said, some of these emphasize the variable with respect to which we're taking the derivative. All right, so that's the general notation for the derivative. Now let's look at how do we modify that in order to emphasize that we're talking about the derivative at a specific x value. So, again, I said to think of x as fixed, but here we're going to really emphasize that x is fixed, and we're going to let x be fixed at some value which we're going to call a. So the derivative notation for being evaluated at x equal a, well, that would be f prime of a. So we see that there. And then also we have our dy dx, and then what you can see what we've added here is that vertical line, and then at the as a subscript x equals a. And that's similar throughout. You can see here d over dx of f of x, and then the vertical line again, and then the subscript x equal a tells you, okay, we're taking the derivative and then we're going to evaluate it at x equal a. So pretty, not too bad, that's fairly simple. And then y prime of a, I think that's pretty obvious. And then again, if you use the capital D notation, it's the same thing. You just tack on a vertical line and then indicate the specific x value of interest. Okay, so there's just a little bit of notation there. And now let's talk about how do we interpret the first derivative. And at this point, if you've watched the previous videos, you should have some idea of how we interpret that. But just a couple of different ways to look at this. And again, here a is some fixed x value. And so 1, it's the slope of the tangent line to the curve y equals f of x at the specific point a comma f of a. And that's probably the most common interpretation. And you can relax a little bit there with number 2 and just say it's the slope of f of x at x equals a. And so when you say slope of f of x at a specific x value, at the point where that x value is a, then we're really talking about the slope of the tangent line, but that's just a little more relaxed way to say it, I guess. Number 3 here we have it's the rate of change of, let me just say with 3 and 4, they're basically the same except for with 3 we have f of x here, and with 4 we have y there. So basically it's the rate of change of the dependent variable with respect to, in this case, x, which is our independent variable. And it's an instantaneous rate of change, so at the point where x is equal to a. Okay, so that's just a couple of ways to the interpretation of the first derivative. Okay, so now we've talked about notation and interpretation. And again, if you have questions about this, I'll be available in my office. So you can email me or drop by, or we can set up a Zoom session, anything like that if you have a specific question. All right, so now let's look at an alternative definition of the derivative. And so it's basically the same language here, the derivative of a function at, every x value for which this limit exists, but now we're looking at a limit that's just a little bit different. And if you notice, this expression that we're taking the derivative of, you may recognize that as basically a slope formula. So if you look at the note here, this expression, f of z minus f of x over z minus x, that is the slope formula between the 2 points. First of all, x f of x, that's here, and then z f of z. So that's the idea. We're just taking 2 different points, and we're considering x here to be fixed and z to be variable. So z can vary, but we're thinking of x as fixed. And so it's just the limit as your z gets closer and closer to x of that slope formula, basically. And that that makes perfect sense. And that this is a valid definition of the derivative. And so if you compute the derivative using either definition, you should get the same thing, because the derivative of a function is what it is, whether you choose to go with the original formula or with this alternative formula. And so we're going to go back to our example, f of x equals x to the third, and use this new alternative definition to see that, to show that we can use that to get to what we got before. And if you recall, the derivative of f of x equal x to the third is 3x squared. So we should see from this alternative definition, we should still get f prime of x equal to 3x squared. Okay, well, let's see. Let's start, directly from this alternative definition. So f prime of x is equal to, this limit of this slope formula. So straight from the alternative definition. And then f of z, of course, is z to the third. And f of x is x to the third. So you can see them just plugging in there. And so at this point, you need to remember, right, because in this numerator, we've got the difference of 2 cubes. And so you need to remember that formula. And so going from this step to this step, what I'm using is the difference of 2 cubes. And if you don't remember that formula, well, it's right there, right? Z to the third minus x to the third, well, that's equal to z minus x times this quadratic, z squared plus zx plus x squared. And then we're taking the limit of what we had before. So we've still got in the denominator, we've still got the z minus x. Okay, so, well, it's obvious what the next step is, right? Because at this point, you know, the z minus x cancels out with the z minus x. And that's what we need because that's the that z minus x in the denominator is what is causing, you know, all the problems. That's what's giving us that 0 over 0. And so once we get rid of that, then we just have the limit as z approaches x of this part that's left. And from there, we can plug in. Now remember, we're letting z approach x. So we're going to plug in everywhere we see a z, we're going to plug in an x. Okay, so then that's going to be x squared plus x times x plus x squared. Well, that's just 3x squared. And so there again, we see using this alternative definition that, you know, we've confirmed again that the derivative of f of x equals x to the third is in fact f prime of x equal 3x squared.